Hi. In this video, we're going to be talking about the direct comparison test, sometimes just called the comparison test. Now, sometimes we come across a series that isn't nice or even possible to integrate, and we'll start with an example like that. But what we can do is we can compare a series in the same way that we did when we looked at integrals, and we saw if improper integrals converged or diverged. So the general rule is just going to be the same thing for integrals as integrals. We know that if the sum of, say, a sub n from n equals 1 to infinity, remember that n can start at any number. If it is less than the sum of bn, as n goes from 1 to infinity, and if bn, the sum of bn, converges, then so does the sum of an as n goes from 1 to infinity. So what this is saying is if we have something that converges and then we take something smaller than it, then the smaller thing also has to converge. And similarly, if the sum of an from 1 to infinity is bigger than the sum of bn from 1 to infinity, and if our sum bn diverges, then uh, so does the sum of an. Okay, and what that's saying is I have something that is bigger than something else. So I have something that diverges, so it goes towards infinity, and then I have a sum that is bigger than the thing that goes to infinity. Well, then that means that the thing that's bigger than the divergent one has to diverge. So if we're comparing it to something that we know converges, we want to show that it's smaller, and if we're comparing it to something that diverges, we want to show that it's bigger. Okay, so let's jump right in with an example. So let's look at the sum as n goes from 1 to infinity of 1 over 4 to the n plus n. Now let's do some pre-analysis to figure out what we want to compare it to. So as we go out towards infinity, we're really going really far out. What's going to happen is this 4 to the n over here is going to overpower, so it's going to overpower n, right? So as we go out towards infinity, this is approximately 1 over 4 to the n. A side note, if we wanted to use the integral comparison test on this, we can't use the integral comparison test. Because if we tried to integrate 1 over 4 to the x plus x, there's no simple integral, and what ends up happening is if we want to integrate it, we first have to look at a series expansion, which we will get to in a few videos. We'll get to a series expansion, and that series expansion is an approximation, so it's not really all that great because remember that the sum of 1 over n to the first goes towards infinity, but the sum, oh, that was a bad sigma, the sum of 1 over n to the 0.999, like a million times 9, actually converges, right? And this is our p-series test. So approximations aren't so great when we want to test the convergence or divergence of series. So let's use a direct comparison test. So as we approach, going back to our original one, as we approach infinity, the 4 to the n overpowers n. So we're actually looking at 1 over 4 to the n to something we want to compare it to. So let's go ahead and show that this first converges, right? So this converges by the geometric series test. Okay, remember that it is a geometric series. We can rewrite this as the sum of 1 over 4 all to the n. And if this were our p, we have p is less than 1. So that tells us that this converges. So this converges. So what we want to do now is we want to show that 1 over 4 to the n plus n is less than 1 over 4 to the n. Because if this guy converges and this is smaller than it, then this one will also converge. So let's go ahead and do a little bit of analysis here. We have 1 over 4 to the n plus n. This is always going to be, the denominator is always going to be bigger than the numerator. So 4 to the n plus n is always going to be bigger than 4 to the n for n greater than 1, right? So that tells us that 1 over 4 to the n plus n is going to be less than 1 over 4 to the n. So we immediately have what we want. It's less than 1 over 4 to the n for n equals 1. So you might be asking now, well, what about n equals 0? Because if we look at our original sum here, we can actually start at 0, which was the problem I had written down and carelessly wrote down 1. Well, what about the 0? And the answer is we don't really care about the 0. In fact, we don't care about the first term if it doesn't match. We don't care about the second term, the third term, the 10th term, the 100th term, the millionth term, the billionth term. We don't care about any of those as long as our condition is met eventually for everything past that point. So we only care about the tail end. And the first billion or trillion terms, when we add them together, it might be a really big number, but it's still just a number. And that's what we really care about. We have a number plus something as we approach infinity. We care about that tail end. And if that tail end converges, then the whole thing converges because it's just going to be a number plus another number. So by the direct comparison test then, since each one of these is less than that, what we have is 1 over 4 to the n plus n as we sum up from 1 to infinity is going to be less than the sum from n equals 1 to infinity of 1 over 4 to the n. Right? And we don't care about that 0 because it's just part of our initial set. It's more like the head of the animal instead of the tail. And since this converges, we have that by the direct comparison test. So by the direct comparison test, the sum from n equals 0 to infinity, 1 over 4 to the n plus n converges. And so that's how we show that something converges if we know that something else similar to it converges. Now let's take a look at divergence. So let me just get a little bit of space here and we'll talk about some divergence when we have a clean screen. So now let's look at the sum of n over n squared minus cosine squared of x. And n here, or cosine squared of n. So we're going to look as n goes from 1 to infinity. Could we start at 0? Yeah, but then we just have 0, right? It's 0 over 0 minus cosine of 1. Cosine of 1, I think, it's positive, so we don't have to worry about squaring it. It's going to be 0 over a number. So we can start at 0, but we really won't gain anything from our series. Now, as we approach infinity, uh, n over n squared minus cosine squared. So as we go to infinity, n squared is going to overpower cosine squared. So what we essentially have then, as we get really, really big, is we have the sum from 1 to infinity of n over n squared, which is the same as the sum from 1 to infinity of 1 over n, which we know diverges because either the integral test will tell us that it diverges, or the p-series test, or we can just know that the harmonic, Harmonic, series diverges. Okay, so let me just go ahead and show the whole thing. So we have a divergent harmonic series that we want to compare it to. So if we look at n over n squared minus cosine squared of n, this is actually going to be greater than or equal to 1 over n, right? And to see that clear, let's just call this n over n squared, which is the same thing as 1 over n. And the reason is cosine squared is always positive. This is always greater than 0, or greater than or equal to 0. And when it's 0, these two things are equal. But when it's not 0, the denominator is actually going to be smaller. So this thing is actually going to be smaller than this when it's not 0, and every integer 2 pi, it's never going to happen where we have an integer multiple of pi, so it's actually technically always greater than 0. But we can say it's greater than or equal to 0, which means that this guy here is going to have a smaller denominator than this guy. So this thing on the left is actually going to be always bigger than or equal to the thing on the right. So now we can say from here that the sum of n over n squared minus cosine squared as n goes from 1 to infinity is actually greater than or equal to the sum as n goes from 1 to infinity of 1 over n. And this one diverges. So that tells us by the comparison test, that the sum, a bad sigma, the sum as n goes from 1 to infinity of n over n squared minus cosine squared of n also diverges. And that's it for the direct comparison test. As always, if you have any questions, comments, or concerns, leave them down in the comments below, and thank you for watching.